script. I guess let's start with the introduction, then students may join in. We'll take around 5 minutes for the introduction. So, welcome to the week 7 live session of the course NPTEL NOC25 EE-39. The course is titled Fundamentals of Semiconductor Devices and is taught by instructor Professor Digvijay Nath from IIC Bengaluru. I'll be the TA for this session. And as usual, the schedule for these sessions is every Sunday, 3 p.m. to 5 p.m. Okay. Feel free to reach out to me via email if you have any query regarding the session. So let's now quickly go through the guidelines. In case you have any query, you can ask it in the chat window or you can raise your hand. When you don't intend to speak, please make sure that your microphones are muted so that there is no disturbance. And I would appreciate your cooperation to make this an interactive session. I'm assuming that you have a scientific calculator with you, along with pen and paper. And as far as the session recording link is concerned, the recording link and the lecture notes will be shared by the NPTEL course team in the due course of time. So the prerequisites for this session include the lectures that we taught in last week, okay, which covered the following topics. You were introduced to MOSFET, right, metal oxide semiconductor capacitor. Then you were, shown how the CV characteristics of MOS look like for different frequencies. How do they look like for high frequency? How do they look like for low frequencies? And then you were also, you also read about the threshold voltage and MOS CV in more details, right? These were, what should I say, the broad topics in the last week lectures. Does anyone have any doubt with regards to these?
Kindly repeat, sir, on threshold voltage.
Threshold voltage. What specific doubt do you have in threshold voltage?
Actually, when threshold voltage does work.
Let me qualitatively explain it. See, if this is your, so this is your metal, this is your oxide, right? Let this be semiconductor, right? This is your oxide insulator. It's a semiconductor, okay? Let's make it P-type, okay? So this is doped with acceptor ions. This is metal. Right. Now, this is your gate terminal and let this be your body terminal. Okay. So, what is threshold voltage in case of MOS capacitor? Okay, firstly, tell me one thing. If this is your P-type semiconductor, what happens if I apply a negative gate voltage? What happens if I apply negative gate voltage? in this system. What are majority carriers here? Did you go through last week lectures?
Positive.
I'm saying, what are the majority carriers in a p-type semiconductor? They're holes, right?
Close, sir.
Right. That's why it's p-type, right? So you have holes, and uh, when you apply a negative gate voltage, the system goes into accumulation, okay, for this p-type semiconductor. So you'll have holes getting accumulated, right? This. You have holes, right? This is for this case, right? When gate voltage is negative. This was your case one. Now case two, when you
Yes,
apply,
increase, sir, and M decrease.
sorry, I did not get your point. Could you please come again? When your gate voltage is positive, right? But less than your so-called threshold voltage. Okay, first wait, what is VTH? What is VTH?
Threshold voltage, sir.
Yeah, but what is this threshold voltage equal? Suppose you are given doping, right? Suppose you are given doping of this p-type semiconductor, then what is this threshold voltage equal to? Can you compute this threshold voltage if doping is provided? So let's answer that. You can, right? Your VTH is equal to 2 phi f. I mean, if we go by the classical definition, right? And your phi f is your bulk potential. So this would be 2 kT by Q ln of, here it's p type of, so this would be Na by Ni, right? This would be the value of this 2 phi f, which we define as threshold voltage. And what is special about threshold voltage? You went through lectures, right? So what is special about VTH? Why did we define VTH in first place?
Sir, Ni increase. When Ni increase, then threshold
When you
voltage
increase what?
decrease. Ni
Ni.
or Q. Ni or Q. T. Depending on T, Q, and Ni.
No. I mean, you're going in a different direction. I'm not asking that. I'm asking, why did we define VTH? This is, don't confuse this with thermal voltage, VT. Your VT was this KT by Q. I'm not asking that. This time it's VTH, right? Threshold voltage. Your threshold voltage, I said we define it as 2 phi f, right? Where your phi f is the bulk potential. I'm not sure what notation you have been taught in your course content, but phi f is bulk potential, right? Given by KT by Q ln of Na by Ni, right? And this phi f is the difference between your intrinsic EI and Fermi level, right? If this is your, say, EV, This is EC. Let me draw a neat. Because this is EC, right? This is EV. Right? What is this? EI, right? And what about this? Why did I draw EF below EI?
Due to sir P type.
Yeah, since it's P type, that's why your Fermi level would come below EI, right? And what is phi F now? Could you please unmute yourself, Sandeep Jamkar?
Sorry, just a moment.
Thank you. So now, what is this phi F that I just wrote as KT by Q ln of NA by NI? What is this phi F in terms of energy difference in this band diagram? Yes. Is the difference between your this intrinsic
Sir
level,
KT by Q ln.
and that is what I wrote it mathematically, right? I'm telling what is this phi F equal to in terms of energy difference. So I'm giving hint from my side, right? So this phi F is equal to energy difference of two levels. What are those levels in this diagram? Remember, your EG is the difference between
EC by
EC and
EF.
EV.
EC
What?
EC minus EF.
No,
EC
EC
minus
minus
EF.
CF. No, EC minus CF. No,
Uh,
Is it between intrinsic Fermi level and intrinsic level and the
the
Fermi
fermic
level?
level. Yeah, this is your phi. By the way, since two of you came late, so the question that Sanjeev had was with regards to threshold voltage. So that's why I'm illustrating that point. Okay. So now this is your phi f, right? And VTH is 2 phi f. So let me again state the question. Maybe you two can answer it. What is so special about VTH? I mean, I said we define it to be 2 phi f, right? But what is so special about VTH? Why was there need to define this voltage? Any idea?
It's the threshold voltage. That's the minimum voltage. I mean, it's a material specific minimum
Agreed,
voltage
it's
that.
material specific in the sense that it depends upon its doping. Fine.
Yes.
So far, good. But why did we need to define a particular value? Right? This VTH is particular value of VG, right? This is particular value of VGB. What is so special about this 2.5? So at your VGB equal to 2.5, what happens is, suppose your doping in the bulk is Na, right? I mean, you will dope this P type. There would be some doping of this P type semiconductor. That's why it's P type, right? So it would be doped with your acceptor ions. Let that be, suppose, X, right? So at VG, at your gate voltage, when your gate voltage is equal to this particular value, threshold voltage, or I should say 2.5, the firstly, when you apply a positive gate voltage in this system, what will happen to the surface? Let's say I made gate voltage slightly positive. What will happen? When I apply negative gate voltage, holes get accumulated at the surface, right? Because they are the majority carriers in a p-type semiconductor. But what
Threshold
happens if
voltage, sir, increase, sir.
what will increase?
Threshold voltage.
No, threshold voltage won't increase. How will
Oh,
that increase? I mean, that is material specific, as one of the students
degrees, sir.
just threshold voltage won't be. I mean, how will that change, right? Threshold voltage is particular value.
Degree.
Threshold voltage is a particular value of gate voltage, right? I mean, that won't change if you change the gate voltage. But what I'm saying is, when you make gate voltage slightly positive, what will happen to the surface? When it was negative, holes got accumulated, right? And when it's positive,
It'll be exactly opposite of that. You'll have more of
it will
electron
be.
concentration.
But before that, something else will happen, right? I agree. I mean, when your gate voltage is abundantly high, I mean, sufficiently high, ultimately electrons will get, I mean, populated at the surface. But before that, something else will happen, right? Because electrons are minority carrier in a p-type semiconductor. Did you get the point? Okay, think in this way. When we applied negative gate voltage, holes got drawn towards the surface, right? Because the field was in such direction. When we apply a positive gate voltage, what will happen to the holes?
They'll be repelled.
They will be repelled. And if the holes are repelled, what we will be left behind with?
With negative ions.
Negative ions,
I mean
right?
electrons.
Yeah, I mean, no. Ions, acceptor ions will have, because ions cannot move, right? Only free carriers can move.
Mm-hmm.
Free carrier is hole, right? So
Mm-hmm.
holes can move
Yeah, yeah.
and will be uncovered with ions, acceptor ions. So let me draw that. So this you understood, right? Accumulation is simple. And this is what happens when you apply gate voltage that is less than threshold voltage, right? So what happens is we'll have these ions. These are not electrons, but acceptor ions, right? Because it donated, I mean, it donated hole, right? That's why. It sorry, I mean it accepted an electron, right? That's why and gave rise to hole. That's why it's a p-type semiconductor. So we'll have acceptor ions. So what happened to holes was they got repelled away, right? And when your gate voltage, let me write this as well. Gate voltage is positive, but VG is less than VTH. And this region I said is accumulation, right? Accumulation of majority carriers, holes in this case. What is this region of gate voltage called?
Depletion.
Depletion, correct. So this would be your depletion because it resulted in depletion charges, right? It depleted holes and we were left with a depletion region that had acceptor ions. So this is depletion region. Right. Then comes your case 3. Right. In case 3, your gate voltage is, I mean, sufficiently high and your VG is say greater or equal to VTH. Now came this VTH, right? So what will happen at VTH? So as I mean, when I said what will happen when you turn this gate voltage positive, you said electrons will come at the surface, right? So that will happen at a sufficiently high gate voltage. So now as you increase and increase the gate voltage, what will happen to the concentration of electrons at the surface?
Electrons will be moving towards the
Electrons will be moving towards the surface. So what will happen to the concentration of electrons at the surface? That is the question.
more electrons created, so it becomes N-type.
Yeah, I mean, surface nature of the surface would change. So the idea is the concentration of electrons would increase, right?
It means
Keep in mind the electrons, they were minority carriers in a p-type semiconductor, right? And now, as you are increasing and increasing this gate voltage, you are drawing more and more electrons towards the surface, right? Making the surface more and more n-type,
negative.
right? A point will reach when the concentration of electrons at the surface would be equal to the concentration of holes in the bulk. I mean, do you recognize? I mean, or you, do you? I mean, what should I say? Uh, can you visualize this?
Yes, sir.
Right,
Yeah,
because
got it.
concentration of electrons is increasing at the surface, so a point will reach, and that point is your VTH, right? That particular value of VG is your VTH, and uh, let me not go into the details. This is 2,5. One can show via band diagram as well. Take any standard textbook. There you'll see. Wait, I can try to show that as well. Or I mean, I'll include it later. So VTH is equal to 2,5, right? So any other doubt? I mean, this was with regards to threshold voltage because one student had asked a question. Or should we move ahead towards the problems? No questions? Let's move towards the problems then. So this is our first problem today. So you are given a band diagram of a p-type semiconductor of band gap 1 electron volt. A student was asked to fabricate a MOS using the below semiconductor such that it has following parameters. Now, your VTH is minus 0.16 volts, and your COX is 100 nanofarad per centimeter square. Your work function of the metal is 3.87 electron volt, right? Assume that there is no charge within the oxide, and if the voltage across the fabricated MOS capacitor is VTH. Okay, if you are applying VTH, what is the magnitude of depletion charge per unit area, right? So you need to find depletion charge. Let me denote that by QB. Since it's per unit area, I'll use this notation, right? Prime to indicate that it's per unit area. So this is the quantity that we need to find. So how will you approach this? I'll wait for a couple of minutes. Okay, I guess I'll start now. So recall that your depletion charge per unit area, that would be, suppose this much it's depleted, right? Let me call this W dip, right? And what is the doping concentration of this acceptor ions? Yes. What is the doping concentration of acceptor ions? Na, right? We are just uncovering the ions. The concentration of the ions would be same.
Yes, sir.
Do you agree? Right? This would be Na. So now this is W dip. This is Na. So what is this quantity? What if I multiply your Na with W dip? What will this give me? If this quantity gave me acceptor ions per unit volume, what will this quantity give me?
Charge per volume.
This quantity would give me acceptor ions per unit area. Right? You're just
Okay.
multiplying this by
Na by
one dimension, right? This was your carriers per unit, sorry, I mean ions per unit volume, right? Per centimeter cube unit. Times you are multiplying this by W depth, depletion width. This is in centimeter. So this would be centimeter per centimeter square, right? So this is uh, Na ions per unit area. Now, what is depletion charge? Your depletion charge per unit area, right? Since we were interested in QB prime, that was depletion charge per unit area is Q times, right? Because this is just a number, right? You need to multiply this with Q, right? Only then will this be charged, right? So what are the units of this quantity? The units of this quantity would be coulomb per centimeter square. So this is charge per unit area, and it's depletion charge per unit area precisely. So I'll write Q Na W dip, right? And now, what is my, wait, what is psi is, wait, since we are asked to compute the voltage, right? Say, we need to compute uh, if the voltage across the fabricated MOS capacitor is threshold voltage, right? When this is threshold voltage, what is psi s is equal to what? Sorry, I just think I made an error. When I defined VTH, I said it's equal to 2,5, right? This is actually surface potential, which is 2,5. Sorry for the typo or mistake. Okay. Was surface potential introduced in this course?
I'm sorry, I still have to go through lectures, but I had taken another course by ISWDP, and there we had a lecture on this, but not sure about.
Right. Surface potential is actually a measure of your band bending, right? So
Mhm.
let me correct my sentence, what I just had said earlier. So I said, I'll say it again so that it's clear. When your VG is VTH, your psi-s, which is a measure of your band bending, psi-s is 2.5. That is what actually it is. I mean, I just messed up. I just said that your VG is equal to 2.5, and that is the value of the gate voltage, that threshold voltage. That is not true. Gate voltage is a particular voltage. I mean, threshold voltage is a particular value of gate voltage at which surface potential is equal to 2.5. Okay, now it's fine. Is this clear? Sorry for the typo. The rest of the things remain same. I mean, this phi f definition is same. I mean, 2.5 would again be 2 kT by q ln of Na by Ni. Right? So I'll write it again. This psi s would be 2 kT by q ln of Na by Ni. Okay. So this is QNAW dip. So now let me write this. This would be Q from potential balance. You know that your VGB is equal to VAB plus psi-s plus psi-ox. Right? This is potential balance in the MOS capacitor system. So now, what is your VGB? Your VGB is your VTH. Right? So this is VTH. What is VFB? VFB in this case is phi-ms, right? Why VAB is phi-ms in this case? Because there is no charge within the oxide. Had there been charge in the oxide, then we had to, uh, I mean, then it wouldn't have been phi-ms. There would have been minus q ox by, sorry, minus q ox prime by c ox prime as well. So for this, when you don't have charge within the oxide, your VAB is simply phi-ms. Then what is your psi-s? Your psi-s is your 2.5, right? And you can write your psi-ox as gamma square root of psi-s, right? And if you write that, this will be gamma square root of psi-s, which is 2.5, right? Done. And VTH, we know VTH in the question is given that VTH is equal to minus 0.16. And work function of the metal is also provided. What else? See, work function of the metal is given, right? Can you compute the work function of the semiconductor from this diagram? What is the work function? Firstly, what is work function by definition? It is the difference of your Fermi level from the vacuum level. Okay. And in the question, it's already given that on the metal side, your
0.2.
work function. Wait, first, let me complete the sentence. It's given that your work function of the metal is 3.87 electron volt. Let me break. Actually, why I'm doing this is because phi ms is phi m minus phi s, right? And then it's 2 phi f plus gamma square to phi f. Now, phi m, it's given that it's 3.87. electron volts, right? Yeah. Now, what is phi s? What is difference of this from this? For that, you need this. What is this? Band gap is 1 electron volt. This is 0.5. This will also be 0.5. So what would be this?
0.3.
0.3.
0.3.
And if this is 0.3, then what would be this?
5 electron volt.
No, 4.8, right? I mean, I need to take it up to this point,
Okay.
right?
Okay,
Because
yeah.
your
Then
work
it's
function is Fermi level from the vacuum level. This much is your phi s. So this is 4.8, right? So this is 4.8 plus, then 2.5 we can take as 0.6. I mean, 0.6 to 0.8 value. That is the typical range that we take if it's not given. Plus gamma square root of 0.6. That is 0.16. And if you'll do the maths, your gamma would be, gamma comes about as what, 0.17 by square root of 0.6. We can verify this thing. Okay. Now this is gamma and it's known as body factor. And there is alternative uh, relation of your depletion charge in terms of this gamma. What is that? That is as follows. Your gamma, okay, sorry, your depletion charge, right? Your QB prime is equal to gamma square root of psi s times Cox prime. Okay. What is psi s? It took that as 2.5, right? Remember, because it's at the threshold voltage. Given that, I mean, your voltage is threshold voltage. So your surface potential would be 2.5, right? I already discussed this after correcting myself. Now, let me put in the numbers. Gamma is this. So this is 0.17 by square root of 0.6 times, what is square root of 2.5? I already said, right? Usually take the value 0.6 to 0.8 if it's not given. So this is what this is. 0.6, right? Because psi s is 2.5 and 2.5 is 0.6. Cox prime is already given. What is Cox prime? 100 nanofarad. So if you do the maths, your depletion charge density, right, QB prime would come as 17 nanocoulomb per centimeter square. Is this clear? I mean, I agree that it was a little involved, but if there is any doubt or if I should repeat anything, you can let me know. I'll do that. So the idea was we had to compute work function of the semiconductor from this band diagram to get this phi ms, which was VAB because there was no charge in the oxide. Because had there been charge in the oxide, then your VAB would have been phi ms minus Qox prime by Cox prime. Then we took psi s as 2.5 because we were operating at threshold voltage. And we took the value of the 2.5 as 0.6 because typically we take it as 0.6 to 0.8. And yeah, that is it. Had you were given the value of the doping, Why did I write 25F as 0.6? I said your phi f is the difference between EI and EF, right?
Yes, sir.
If it's difference between EI and EF, what is the difference between EI and EF here?
0.3, sir.
0.3. And what is 25F?
0.6.
Got the point? That's why it's 0.6, right? Is it clear then?
Yes, sir.
Yes, sir.
Okay. And move on to the next question. So now with reference to the previous question, what is the value of the phi ms in electron volts? So what is the value of the phi ms in electron volts? Your phi m was given in the question, right? Phi m was this, which was 3.87 electron volt. What was your phi s? Your phi s was this, right? 4.8 electron volt. What is phi ms? Phi m minus phi
1.07.
s.
1.07.
What?
1.07, ma'am.
No. You need to do this, right? 3.87 minus 4.8. What will be that? Electron volt, obviously.
Minus 0.1.
Minus
Minus
0.1.
0.93.
Yeah, this
Minus
is the right
0.93, the second option.
minus 0.93 electron volts is the correct option. So now let's move ahead. Consider an ideal MOSFET with following parameters. It's given that the semiconductor is P-type. Cox is 1.7 microfarad per centimeter square. At Vg equal to 2 volt, it is under strong inversion region, right? So this is uh, at this particular value of Vg, it is under strong inversion. If your inversion charge density at Vg equal to 2 volt is okay, Qi prime is given at this Vg equal to 2 volt, which lies in this strong inversion region. So what will be the inversion charge density for Vg equal to 4 volts? So obviously Vg equal to 4 volt will also lie in strong inversion region because it's greater than Vg equal to 2 volt. If Vg equal to 2 volt lied in strong inversion, then Vg equal to 4 volt will also lie there. If I draw this Qs versus Vg, you'll have and then there would be electric and current, and then it would be right. What is this? This is VTH, right? What is this? VAB. I actually divided this whole into three regions, right? This is your region one. This is your region two. And then you had region Great. What does region 1 fall in? Which region is region 1? Considering that this is a p-type semiconductor. Remember negative gate voltage in a p-type system. What would this be? Will it be inversion? Will it be depletion? Will it be accumulation? This is the same system, right? When you applied negative gate voltage, you concluded, right? It's an accumulation region. So again, so this region 1 would be your accumulation region,
Inversion.
right? What about region 2? As you increase gate voltage beyond VFB,
Depletion, sir.
yes, this would be depletion. What if your gate voltage is greater than threshold voltage? Inversion,
Inversion, sir.
right? Now, does anyone remember the expression for your inversion charge density, Qi prime? See, what is the slope, value of slope here and here? What is the value of the capacitance in accumulation region? Cox prime, right? Remember, you see something like this. It's flat till here, then this falls, and then this rises, something like this. So it's Cox here and here. In other words, the slope of this region and this region is Cox prime. Okay. So your Qi prime is Cox prime times your Vg minus Vth, right? What is the slope of this? Differentiate this with respect to Vg, you'll again get Cox prime, right? I've subtracted Vth because this is valid only beyond Vth, right? Before Vth, this is depletion, and you cannot use this equation. That's why this minus Vth. This is valid only for the values greater than Vth. Okay. Now, in the question, it's given that your inversion charge density, see, at Vg equal to 2 volt, it is under strong inversion, right? So there would be some point here in region 3, right? Suppose this is a point. Right. And this, suppose, is your Qi1. And then suppose now you have to determine what is the inversion charge density at gate voltage equal to 4 volt. Suppose gate voltage equal to 4 volt lies somewhere here, right? This is 2 volt and this is 4 volt. This is QI1 and this is QI2. What is QI? Wait, now we need to find QI2, right? I can write that your QI1, or I should say QI2. Right? This particular value I know, right? What is this? 2.2 microcoulomb per centimeter square. What about this value? This is equal to this. Slope I know, right? This particular distance I know, right? This is equal to 2. So can I find this? I can, right? So Cox is the value of the slope. So if I multiply, see, let me draw this. This is, suppose X is what we need to find. This is 2, right? Because it's this distance. So what is X by 2? Yes, what is X by 2?
Tan theta.
Yeah, and tan theta is your slope, right? So X by 2 is your slope. And what is slope? Cox prime. I already discussed, right? For this region and this region, your slope is Cox prime. So now X by 2 is Cox prime. So what is X then? Two times Cox prime, right? So your, and what is X? Your X is QI2 prime minus QI1 prime. So I'll write following. My QI2 prime would be equal to my QI1 prime plus 2 times Cox. Do you agree? Do you agree or not?
Yes, sir.
Correct. What is QI1 prime? That is 2.2 microcoulomb per centimeter square. Plus, what is 2 Cox? 2 Cox is 3.4 microcoulomb per centimeter square. What is sum of the two? 5.6 microcoulomb per centimeter square. Right, and this is your QI2 prime. Is this clear now? Do you agree? Right, Cox prime was already
Sir,
given.
how 3.4?
Double of this, right? Hope that answers your question. Now, let's move on to the next question. Now, we have following question. In an ideal MOS capacitor, uh, it's fabricated on a P-type silicon substrate. Okay, and it's having a doping concentration of, I mean, like septarine doping concentration is 10 to the power 16 per centimeter cube. The value of the work function phi s of the silicon substrate at the room temperature is what? This will be explanatory from the band diagram. Okay, let's draw the band diagram. This is E naught, this is EC, this is EV, right? And what is this? This is electron affinity chi, right? In fact, Q chi, no chi, it's fine. EI would lie somewhere here. And this is EI. And this would be EF. Again, why I have drawn EF below EI? Because it's a
P-type.
P-type substrate, right? That is the reason I did so. Now, this particular difference, EI minus EF is phi F, right? And what is phi F equal to? The bulk potential, right? This is KT by Q, ln of Na over Ni. What is KT by Q? This is thermal voltage. And at room temperature, you can take it as 26 millivolt, right? So I'll write it as 0.026. And then you have ln of this, right? This 10 to the power 16 by Ni, we can take as this value, right? So if you'll do the math, your phi f would be, do check it at your end, right? Your phi f would be this particular value, 0.35 volts. So now what about phi s? What is phi s? The work function of the silicon substrate. I already said that we define it as the energy difference between your vacuum level and the Fermi level. Right, this is your Q phi s. This is your Q phi f. So if I had to write, I'll write phi s would be equal to your chi, right, plus this plus this plus this. And what is this? What is the difference of this EC and EI? This is you got the question? Did you get it? What is this? If this is your band gap, what is this?
EF minus EC.
Please, again.
EF minus EC.
No. I'm saying about this. In this particular, let me draw this. This. What is this?
So what function, right?
No. Work function is this whole thing.
EF minus
Oh.
EC.
Sorry.
And I'm asking about this. What is the difference between EC and EV? First, let's break the problem. What is the difference between EC and EV? This is your band gap, right? EC and EV are
Yes, sir.
separated by band gap. And what is EI is at the middle of the band gap, right? I mean, approximately, it is located at the middle of the band gap. Although it's slightly offset, let's not get into those details. But EI is at the middle of the band gap. So what is this? Half of what?
Band gap, sir.
Half a band gap, correct. So this would be EG by 2, right? And this is Q5. So for units consistency, since chi is okay. So let this be Q chi. Okay, there is slightly. Let this be Q chi. And your Q chi is this. So I'll write in terms of volts everything. This would be chi plus Eg by 2Q. Why I am divided this by Q is because Eg by 2 has units of electron volts. I'll divide this by Q so that it has a units of volts. Or alternatively, what you can do is we'll have Q this side, Q this side. That is also, you can do on this as well. And then it's Q5. And then it's mathematical problem. Q chi is 4.05 electron volt. Your Eg by 2 is 0.55 electron volt. What is Q5? Your Q5 is 0.35 electron. If you sum this over, your Q5S would be equal to 4.95 electron volt. Fine. So that finishes this. Do verify this at your own end. Okay. Make sure you get this value. Now, what about this? In an ideal MOS capacitor has got a boron doping concentration of 10 to the power 15 in the substrate. When gate voltage is applied, a depletion region of width 0.5 micrometer is formed with a surface channel potential of 0.2 volts. Given that your permittivity of free space is 8.854 into 10 to the power minus 14 farad per centimeter, and the relative permittivities you can take as 12 and 4 for silicon and silicon dioxide respectively. What is the peak electric field in volts per micrometer in oxide region? So the relevant formula in this case is that your surface potential size is approximately equal to half of your W dip times your peak electric field, right? So what are the quantities that you know and what is the quantity that you need to compute is you need to compute the peak electric electric field in the oxide region. That is this, right? And this would be 2 psi s whole divided by W dip, right? And that is 2 times what? Surface potential is 0.2 all divided by W dip. What is W dip? And W dip is 0.5. Let's convert micrometer to centimeter, then it would be 10 to the power minus 4, right? And this would give you the value in volts per centimeter, right? I guess it's how much would this be? Can anyone quickly do it? This would be 0.4 by 0.5. What is that? 4 by 5. What is 4 by 5? 0.8, right? No. Let me do it. So this ES would be the peak electric field in the semiconductor interface, right? Semiconductor. I mean, wait, I should first discuss this. You remember at this oxide and semiconductor interface, suppose this is your oxide semiconductor interface. Your this is equal to, I mean, D1N is equal to D2N, right? This is one of the boundary conditions that we use, right? And since your epsilon r oxide is not equal to epsilon r silicon, right? Then that means your EOX prime, sorry, your EOX electric field at the oxide side interface would not be equal to the electric field at the semiconductor side of the interface, right? And but this holds good, right? And what is D? D is your epsilon times electric field, right? And epsilon naught can be cancelled on both sides, and we'll be left with following. Your epsilon naught electric field on the oxide interface would be equal to epsilon s electric field on the semiconductor interface. So this gives us that EOX would be equal to epsilon s by EOX times electric field at the semiconductor side of the interface. Right, what is this? This will have some value, right? And what is this? This is 12 by 3, which will be 12 by 4, which would be 3. So this would be 3 times of this. Right? This comes about as 0.8. What? 0.8 volt per micrometer. That is your case. What would be this then? This particular factor is 3. So this would be 3 times of this. So I can write this would be peak electric field in the oxide region would be 3 times the peak electric field in the semiconductor region, and that would be 2.4 volt per micrometer. Is this clear?
Yes, sir.
So the correct option is this one, right? The peak electric field in the oxide region would be 2.4 volts per micrometer. Okay, then you have this problem, right? Which I think you would be knowing. Just a second.
Yes, sir.
He said 3.
See, third. Just a second, just a second. An ideal NMOS is
Sir.
subjected to a CV measurement with a fast DC sweep and at a high frequency small signal. So, which of the following CV characteristics will it exhibit? Yes, the correct answer is C. And what is this known as? This would be in which mode? Deep depletion, right? I guess you would have heard this term since you readily recognized it. So then what? Then you have this one. Consider a MOS capacitor with a P-type silicon substrate doped to Na equal to 3.10 to the power 16 per centimeter cube. The work function difference 5 ms is given. You need to determine oxide thickness such that your threshold voltage is 0.65 volts. So this is a question on threshold voltage of the MOS capacitor. So what is the relevant formula?
KT by Q ln.
That is 5, right? I'm asking for this. Just a second. Give me a second. What is your VTH for a MOS capacitor?
KT by Q into ln.
That is bias, right?
And Na by Ni.
Remember this potential balance equation? Yes, I'll copy this. Right. Now, VGB is VTH. What is VAB in this case? Assume that there is no charge in the oxide and your VAB is 5 ms, right? I'll write this as 5 ms. What is size? Size you can write as 2,5, right? Right? Because your surface potential is pinned beyond this threshold voltage. You can take the value of the surface potential at the threshold voltage is 2,5, right? By definition. What about Psiox?
Rho root 2 5
Yes.
5 gamma root 2 5
Gamma square root of psi s, right? That is what we can use Psiox as. I write that gamma square root of psi s, but my psi s is 2,5. And what about gamma? What is gamma equal to? Gamma is your body factor, right? Your gamma, note it, that it's equal to square root of 2q epsilon s Na whole divided by Cox. Now, what do we need to determine? We need to determine this oxide thickness, right? What is Cox prime? Cox prime is equal to, yes, what is this? Epsilon Ox by what? What should I write here? What is oxide capacitance equal to? Oxide capacitance per unit area. Okay, what is the expression for a parallel plate capacitor? It's epsilon A by D, right? So what should I write in place of D here? Since it's capacitance per unit area, it would be epsilon by D. What should I write instead of D? It's Tox. Okay, so Cox prime is epsilon ox by Tox. Now, if you substitute this here, right, Na, you know, Tox is something that you need to determine. So in gamma, the only unknown is Tox. Phi f, do you know phi f? Do we know phi f? What was phi
Yes,
f?
sir.
Does we know phi f, right? Why do we know phi f? Because the doping is given. Since Na is equal to 3 into 10 to the power 16 per centimeter cube, so we know phi f. So this is also something that we know. Gamma has only one unknown, Tox. What about phi ms? Do we know phi ms? Yes. It's given that phi ms is minus 1.13 volt. What about threshold voltage? It's given that threshold voltage is 0.65. So in this whole equation, the only unknown that is left is what? This, because this has this Tox. And that is what we need to determine. I'll leave this as an exercise for you. I mean, I gave you an overview. What would be the recipe for this? Find the value of the Tox that satisfies this. Okay? It's straightforward. I mean, this is a mathematical problem
Sir,
behind
what
this.
value should be, sir? What value
What
should be, sir?
value for
What
what? I
value
mean,
should be?
what
Yes, sir.
value should you use what? For what?
Yes, sir. Yes.
That is something that I'm leaving as an exercise, right? I'm asking you to find Tox. See, I'm saying your Cox prime is epsilon ox. Right, instead of Cox prime, you can write epsilon ox by Tox. in this equation, right? This is your gamma,
Okay, sir.
right? You substitute this here. The only unknown left here is Tox. So you can find Tox by manipulating this equation mathematically, which I assume you all can. So I'll move ahead. So rest of the questions I'll leave as an exercise. So you have around 3 questions as an exercise, and then you can consider doing problems from the peer as usual. So does anyone have any other question? If not, we'll
Sir,
be ending
kindly
this.
repeat on T of
Okay, this problem, what do you
T of
want me
sir.
to repeat?
Sir, T of C of by T of sir. T of
Okay, this equation, how does this come about? Are you asking this?
T of by T of the T of what do you mean?
I mean, I did not get your question. Could you come again? Are you asking how does this formula come about?
Yes, yes, sir.
I mean, this is pretty straightforward. This is oxide capacitance. The oxide capacitance would be equal to, consider that as a parallel plate capacitor, right? Two plates. The oxide is between two plates. What is the permittivity, relative permittivity between the two plates? Sorry, permittivity between the two plates. The permittivity of the oxide, which is epsilon ox, right? You remember this? This you all would remember, right? C is epsilon A by D. We all did this in 11th, 12th high school physics, right? C is epsilon A by
Yes,
D.
sir.
Yes, sir.
I'm
Yes,
saying
sir.
Yes,
Yes,
sir.
sir.
what is C by A? C by A is epsilon by D, isn't it?
Yes, sir. Got it,
Yes,
sir.
sir.
Right. And this C by A, I'm using this because I'm interested in oxide capacitance per unit area, right? Oxide capacitance per unit area. So that would be permittivity of this material. So in oxide, the material is oxide, so it would be epsilon ox, and it would be thickness of the oxide. D would be thickness of the oxide. That's why this formula is so. I hope this answers your query.
Thank you, sir.
Done?
Got it.
Okay. Thank you. We'll be ending the session then, okay? Thank you and have a nice day.
Good evening, sir.